Hey, Matt,
Hey, Mike.
would you like to do a complex or maybe not complex podcast episode?
That's non-deterministic, but yes.
All right, let's jump into it. Welcome to Hacking the Grepson. I'm Mike. He's Matt. Last episode, I talked about music dev, and I talked a lot because I kind of brought that issue to the table or idea to the table. But this episode, Matt's going to do more of the talking because we're talking about the concept of P versus NP. Now, I'm assuming that's peanut versus not peanut, but I feel like it's probably more complicated than that. So I'm going to let Matt start us off.
Yeah, you're right. It's all tied into peanut allergies.
Oh, okay.
No.
I get it now.
So, yeah, in order to discuss the concept of P versus NP, I have to introduce a few other concepts first, just so that we have a common set of a common language that we can speak as we're talking about this.
Okay.
But before we dive into that, just kind of as a real high level, P versus NP is it's a very theoretical type of situation. It's actually more studied by mathematicians, I think, than computer scientists, but it certainly overlaps significantly. In fact, I've actually seen this in popular media on the show Numbers, if you remember that show.
I love that show, yeah.
The mathematician guy whose name I'm blanking on has like a breakdown in one episode, and he just like goes off into the garage and is trying to solve some unsolvable problem. That's this problem, is what he's trying to solve. He's trying to prove that P equals NP. Because if it is, that opens up a whole new world of computation that we can do. And if it isn't, well, then things stay the same.
So this is really like the discussion of whether so right now we can't prove nobody can prove that P equals NP, so we're left with P does not equal NP.
It is not determined at the moment whether or not it does or not. So
Okay.
the general assumption is that it probably doesn't, but it might. And it is certainly not clear. So in order to understand why that's important, we kind of have to define what P and NP are.
Yes.
In order to do that,
Peanuts and not peanuts.
exactly. I need to discuss the concept of complexity. So
Okay.
one of the big differences, I think, between computer science and like just coding is the concept of complexity, and specifically like what's called big O notation. And what all that is doing is it's describing how complex, which is usually basically boiled down to how much time or how much space does your algorithm use, right? So the most basic one is big O of 1, which is constant, right? And all of these are based on the number of inputs, right? So that usually you're talking about n as the number of inputs, right? If I'm searching through a list, like through a big array, and I do it one at a time, I'm going to look at every single one. That I'm going to look at n items, right? If I want to print out every item in a list, that takes n space because it's proportional to the amount of space to store it in the array, and it takes n time because it's proportional to the amount of items in there, right? That's linear. If it took no time, if it was always the same amount of time, regardless of how many, right? Like if I had a function that just printed hello world, but you passed in an array of numbers, but I don't look at that, that's constant time, right? That'd be stupid. Don't do that. But that's
a quick question. Like, since you said this is more of a math thing, is O of 1 y equals x, or is that O of n?
That would be O of n. That's linear. Constant
Okay,
would be
so
more like x equals 5, right? And you just get a
okay.
Yeah.
So basically the number of inputs doesn't change on something that's constant,
or the number
or
of
it doesn't
inputs.
matter how many.
The number of inputs is not relevant to.
Not relevant.
Right.
Okay.
It basically just doesn't matter. Ideally, in a perfect world, we would have constant time access for everything because it's fast. If you've ever used, and I'm sure you have because you do JavaScript, if you've ever used a hash map, that the lookup for a hash map is constant, right? Because it's effectively, and same with an array, right? If you index into an array, the lookup for that is constant. It knows exactly where to go because it's just basically adding a number to another number in memory, and that's constant time. If you have a million item array and you access item 500, or if you have a one item array and you access item 1, it takes the same amount of time, basically constant time. The next most complex thing is logarithmic, which is about the best you can get for most good or most somewhat complex tasks. So finding an item in a sorted array, log n is pretty common for that if you do a binary search, right? You start in the middle. You're like, all right, is my item actually bigger than that or is it smaller than that? And then you look halfway in between those and halfway in between those. And so you don't have to look at every single item to find it because the array is sorted. You have to look at what on the average case is basically log n. Now, there are situations where something could be where you have average case might be log n and worst case might be linear, which is the next one, right? And that's not uncommon. You see this a lot with sorting algorithms. In the best case, a lot of sorting algorithms are like n log n, which is basically linear. But sometimes they can be exponential if the data is ordered in the wrong way. So when we're talking about complexity, we generally mean for the average case, what is this? But we do have to keep in mind the worst case scenario as well. As we're talking about that, just remember worst case and average case aren't necessarily the same thing. So the next one's linear. Like I said, printing out an array, that'd be linear. You're going through every single item in the list. Polynomial, which is P. We have now defined what P is. It stands for polynomial. Is something that can be fine. So if you go back to algebra in your mind and wipe away the terror sweats, you might remember something like a quadratic, the quadratic equation, right? N squared.
Right.
But n to basically any constant number falls under polynomial time. Typically, when people talk about polynomial time, they usually mean it's n squared, right? So if you were to try to, so a lot of sorting algorithms are n squared, right? You kind of go through your list and then you go through it again to find where that item should go. And then you go to the next item in your list and you go through every other item in the list until you find where that item should go. So you're going through the list twice, n squared.
Okay.
But it can go bigger. But that's typically what people mean when they say polynomial. Above that, and so everything we've talked about there, all will finish in a reasonable amount of time, regardless of the size. You know, when you start talking polynomial and you get a really large n, it starts to take longer and longer. But it still will finish. It'll finish in our lifetime. But then you go to the next thing, which is exponential, and that's where you have a constant number, usually 2, but not always, to the nth power, right? And so those could take. You know, you might not finish an exponential problem until the heat death of the universe happens.
Right.
Because it just will not finish in time. Those are very complex problems. They cannot be done in polynomial time, which would be
now,
NP.
I have a question because
sir.
this is reminding me of the advent of code.
Yes.
That we did.
Very relevant.
About the fish that were like growing and checking on them, and the way that I was doing it initially was it polynomial or was it exponential?
It was probably exponential.
Exponential, right. And it was taking like hours and hours and hours to finish, and everybody else was like, no, there's a more efficient way to do this that will get it done, you know, much faster, and it generally involved like using better logic about how I was checking. Like, essentially, I thought I needed to make way more checks on the fish than I did in order to update their values, but I really didn't, and so I had to do a smarter logic or algorithm. So in that case, it was about thinking that something was perhaps P, but it was actually not P?
Correct. So
Ah,
there's one other complexity
okay,
type, and then we can dive into the actual definitions of P
okay,
versus NP.
okay,
And I have never encountered this complexity type, but it's but it's big O n factorial, right? Which is just
okay.
factorial, which would take potentially even longer than exponential because now you're not just going 2 to the n, you're going n times n minus 1 times n minus 2 times n, right? And
Right.
so if n gets real big, that's just huge. And play around with the factorial function on your calculator, you can see how fast that number goes up, or how quickly. Okay,
Okay.
so definitions.
Yeah.
P is any decision problem, which when we're talking about decision problems, really what we mean is like algorithms is pretty much what we mean, right? Sorting algorithms,
Okay.
searching
Yeah.
algorithms. If you've ever heard of the traveling salesman, that comes up a lot when you're talking about P versus NP. But it's just an algorithm to solve a problem, decision problem. So it's the set of all decision problems that can be deterministically solved in less than or equal to polynomial time for all inputs, right? So even when we're talking worst case, in order to be P, it still has to be solvable in polynomial time.
Okay. Makes
NP
sense.
is the set of all decision problems for which an answer can be verified in polynomial time, but not necessarily that the solution can be computed in polynomial time. So the example that Wikipedia uses, and I really
Hmm.
liked this because it worked with my brain, is Sudoku. It's a good example of an NP problem. A solution can be checked in polynomial time, right? If someone handed you a Sudoku puzzle, you could look at it pretty quickly and be like, yep, all the numbers 1 through 9 are in this box and in this row and in this column. There's no repeat, right? You could easily
Oh.
check that. But if you wanted to compute it and you computed it by just brute forcing it, you'd sit there and be like, all right, let's try every single every box is 1. Okay, that doesn't work. All right, now this box is 1 and every box is 2, right? And you would find that that doesn't work. So the solution is not necessarily computable in polynomial time, as far as we know, but it can be verified in polynomial time. So that's NP, and then there's NP.
Okay.
Then there's NP hard. Uh, NP hard problems is the set of problems that are at least as hard as NP problems, right? So they are. NP hard is kind of a nebulous concept that, or not necessarily, but I don't want to go into it too deep. But the reason NP hard comes up is because the really important part of this, when you talk about P versus NP, is NP complete. And that is the set of NP problems, which all other NP problems can be transformed into in polynomial time. So if you have a solution for, let's say, Sudoku, right? Sudoku is NP complete. If you had another problem that's also NP complete, that means you could basically find the solution to that problem using the same algorithm that you used for Sudoku.
Okay.
It's basically a mapping problem, right? You can transform it or map one problem into the others. So that's
Okay.
and then there. If you want to talk relationships, this is where an image comes in handy. Just go to Wikipedia and search P versus NP, and you'll find this image. But basically, we know that P is a subset of NP, right? Because if you can solve it in polynomial time, you can verify the solution in polynomial time. So P fits within NP for sure. We know that NP intersects with NP hard, but it's not necessarily 100% overlap. And that section where it
Hmm.
does intersect is what is typically considered NP complete. Um,
Okay. I get that.
so now, 14 minutes into this episode, we get to what we're actually talking about, which is does P equal NP, right? So the way we would decide this is if there is any NP complete problem that can be solved in polynomial time, right? If we find a solution, then by definition of NP complete, we know that all of the other NP problems can be transformed into that in polynomial time, right? Because that's the whole
Okay.
mapping thing. So
Right.
if any one NP complete problem can be proved to actually be P, then you prove that P equals NP. And what that would mean is that you can take things that, like your fish example, that would take forever and effectively just run them through an algorithm that would, in polynomial time, translate it into your solution. And now you have a polynomial algorithm for what was before, say, an exponential or a factorial complexity problem. And this is a big open-ended question.
Whew.
I learned about this like 20 years ago, and it's still an open-ended question in computer science, but it's a big one.
Mm-hmm.
And the reason is, if you can do that, as you can imagine, things that take a really, really long time or are difficult for computers to do now suddenly become trivial. So if P equals NP, it'd have huge ramifications for things like mathematics. Uh, a
Mm-hmm.
big one is cryptography, right? We bank a
Yeah.
lot of security on it would take a really long time for a computer to compute an AES 256 key, right? Because it's so long,
Right.
right? Your passwords have to be over a certain length because, you know, back in the day, 8 characters might have been enough, but now you want more like 16 to have a,
Mm-hmm.
right? But if P equals NP, you need it to be even longer because now cryptography, we can just break things. Credit cards are going to be really vulnerable, all sorts of stuff. Other places where this can come in to play is AI, into game theory, and into, to tie it into our last episode, multimedia processing, because all of those things are very computationally expensive and they take a long
Mm-hmm.
time. And if we can suddenly do them quickly, it's a game changer. It's like the transistor being invented, right? That was necessary to go from like the
Vacuum
the
tubes.
vacuum tubes to a computer that fits in my pocket, right?
Right.
So there's your concept.
Yeah. No, I mean, I'm not sure I can 100%, say this back to you with perfect confidence, but I do, I do understand it a little bit better. So I have some questions.
Yeah.
Um, so how does one prove that P equals NP?
So the hard part is that, well, no one has, obviously, because otherwise this conversation would
Right.
be over
But how
already.
would you even?
If you did, the way you would do it is you would solve one of the NP complete problems. And I think there's something like 3,000 algorithms that they've found that fall into NP complete. Like it's a large number. It's a non-trivial number of algorithms um,
Hmm.
that fall into NP complete. You would prove that you could solve one of those in polynomial time.
So basically, if somebody like using your Sudoku example, um, you can give someone a Sudoku problem. They take an hour. They figure it out. You can verify that their solution is correct in polynomial time. Big whoop. The hard part is brute forcing it in polynomial time. But if I somehow came up with an algorithm that could solve Sudoku in polynomial or less time,
You would be
that
very
would
rich.
prove that P equals NP.
Yes.
So are there people sitting around and that's kind of their life's work is to solve Sudoku in that way,
Not necessarily
potentially?
Sudoku, but absolutely there are people that dedicate like their lives. You know, their doctoral theses on this. It it's an there are it's a big problem in the computer science and mathematics space, as you can
Hmm.
imagine, based on the consequences that you can that would stem from it coming out. People want to know, and it's been a problem, an unsolved problem for so long that whoever does definitively prove it one way or the other, especially if they did prove that it was equal, is going to be real famous in those circles. And if it's true that it's P does equal NP, they're also going to be very rich.
Well, now, I mean, is proving that P equals NP like exactly as hard as proving that it's not?
So proving a negative is
Like,
difficult. Talk to any atheist friend, and they'll tell you how difficult proving a negative is. It's very difficult. So
yeah,
proving that P does not equal NP has met with just as much luck as proving that P does equal NP, right?
right,
Because disproving a negative or proving a negative is very, very difficult. If you could do that, and there are
right.
ways of doing it, probably you'd use some sort of proof by induction, or you know, again, going back to school, if you think about all the times you had to do mathematical proofs, and you're like, why do I ever need to do this? This is the kind of place where you would need to do that kind of thing. If you wanted to learn, if you wanted to be able to do that kind of thing, this is where you would take inductive proofs and deductive proofs and all those other things and bring them together to form a proof. that these things equal.
Yeah. Is this? I mean, you brought up the idea of the transistor versus like the vacuum tube. I mean, obviously we've made strides in hardware that have allowed us to go from ENIAC to our iPhone. I mean, is this P versus NP like the same kind of leap? And is it like way harder than a hardware version of it?
It's yes, I believe it would be equivalent or more. Like it would be a similar paradigm shift if we were to prove that P equals NP. It would be as big of a paradigm shift, I believe, as the transistor. And I think most people that study this space would agree with that. Would it be harder than hardware? I think it would actually be easier, right? Because people have already solved the problem of how to translate one NP complete problem into another NP complete problem. That piece is
Hmm.
solved. We know how to do that in polynomial time, right? What we don't have is any of those NP complete problems being solvable in polynomial time. Um,
Right.
so if someone did that, right, one person solving one algorithm that could do that, it would basically change the world overnight. Because and the first thing that would go is cryptography. Like that that's going to be the first thing that people attack with this because
Right.
again, the other thing that would be equivalent to this paradigm shift wise, and it has for similar reasons, which has to do with how fast you can get stuff done, is quantum computing. Because
Hmm.
effectively, what quantum computing does is instead of one at a time looking at every option, it looks at all the options at once, and then
Right.
gives you an answer back.
I mean, is solving this problem then like a matter of hardware? Do we just need to throw more hardware and money at it, or is it a logical problem?
It's a logical problem. This requires
Okay.
like this would be a thing that if we could ever get AI to the point of being smarter than us, this is the problem we should seek it on, because
Right.
that would open the door huge. In particular for the AI, right? One of the reasons that AI has not gone where science fiction predicted it would go, certainly not as quickly as it predicted, is that it takes a long time to compute things. So if
Hmm.
all of a sudden, so the way AI works today mostly is just you're throwing a lot of hardware at it, right? Massive parallelization. You got some smart indexing into databases, but mostly it has to do with the hardware got faster and we can afford to have more of it, and the internet exists
Right.
so you can have all those distributed systems talk to each other. But P equals
Right.
NP would make that would reduce the amount of hardware you need, which means if you were then to take the same amount of hardware that powers ChatGPT, right? You take that same hardware and that same algorithm, but you have now are able to do P equals NP, and so it's an NP complete problem, and now you can do so much more on the same hardware, and that's both scary and exciting in my mind.
Yeah. I mean, is this kind of like a thing where we should be, instead of using AI to like make art and taking the human out of the art, instead we should be sicking it on itself essentially to solve this problem? I mean, can we use AI to solve this problem, or is it kind of an issue where AI is not smart enough and it's more just really good at taking large sets of data like LLMs and making new stuff out of it, but not actually reasoning the way we need it to do to solve a problem like this?
Right. I think the the advancements in AI that we've seen in the last couple of years with the language models and all that, I think could eventually lead to being able to um, build a computer system that could do mathematical proofs. I would be shocked if they aren't already at that point for some of them. And if we get to that point where it can do it for a generic mathematical proof, like then it's just a matter of feeding it the right input so that it knows what it's looking for. I I have always thought that that's how AI will ultimately get developed. And Werner Vinge, who taught at the same school I graduated from, but is a science fiction author, has this concept of the singularity, right? And what that
Mm-hmm.
is basically once AI gets as smart as us, it can do the same things we can in the same amount of time, it will just it will be able to improve itself,
Mm-hmm.
and then that thing will be smarter, and then it can improve itself, and it's just going to take off, right? That's the singularity. You hit that tipping point and there's no turning back, and you can't even predict what the world will look like after that because we're not smart enough. So
Right.
AI, if you turn it on itself to improve itself, I think that's where you get an actual artificial intelligence. Um, and if one were to turn it on for, turn it on the problem of P equals NP, and it could prove it, I mean, we've been looking at this problem for like 50 years or something, uh, and no one has proved it yet. But if it could, that'd be a game changer.
Like, what do you think in your professional engineering opinion that P is most likely equal to NP or not?
My gut tells me it's
Putting you on the
probably
spot here.
my
Sorry.
gut tells me it's probably not. Mostly because folks have spent so many years trying to prove this, and
Mm-hmm.
it seems unlikely that that many super intelligent people dedicating that much time to a problem would not be able to solve the problem if the problem is solvable. Um, I'm not ruling it out though. I All it takes is one. All it takes is
Right.
one person, one algorithm, and it all gets flipped. Will that happen? Maybe. Will it happen in my lifetime? Probably not. But if it does, I bet AI is the one that's going to figure it out. Sorry, mathematicians.
I mean, like, for any reasonably hard or complex problem, I mean, the more resources you can throw at it, the better. And if you have something like artificial intelligence, as we know it today, at least, feeding itself plus, parallel, compute quantum computing, it's right. It seems like if it is solvable, that it is a matter of time. It's
Yeah.
not like, oh, who knows? But it's just like how long and how much effort will it take? And then, you listed ramifications, both good and bad, if P does equal NP. I mean, if we can prove that peanuts equal not peanuts, that does sound like some kind of like, matter antimatter explosion badness. Like it doesn't seem like we actually want it to be true because all of in one case it takes things that take a long time not take a long time, which is good in theory, but a lot of things that we depend on, like cryptography, depend on them taking time.
Yep.
So if we don't have that, then we're all just going to have to, be a lot nicer to each other. And I don't know if you've studied humans over the last 10,000 years, but I'm not sure that that's what's going to happen. I've played a few too many Fallout games to believe that. Um,
Yeah, and I think that's a really good point though, right? Is it's not necessarily that it's good or bad. I think this, just like when we talked about AI, I think it is morally neutral. It's what you do with it
yeah,
that becomes problematic, right?
right.
Again, just looking at cryptography and credit cards, right? Like there's a lot of literature out there about basically just destroying the world's economy, or resetting the world's economy by just wiping out debt, since it's all basically kept electronically. It's a major
Yeah.
plot point of both a movie and a TV show that I can think of that I don't want to mention
Mm-hmm.
because it spoils both of
Yeah.
them. Uh, but they're
Yeah.
very similar. Uh, and you know, the anti-capitalist in me is like, yeah, bring it down. But the humanist in me is like, wait, what's that going to mean for people? Because we don't live in a socialist utopia. We live in a capitalist world right now. And if money all of a sudden gets screwed up, that's not good for people.
Right.
In the long term, I think P equals NP would be a boon to society. In the short term, I think it would
Right.
be real scary to live through.
Yeah, it does seem like you said, it's a huge paradigm shift, and it's going to get worse before it gets better. But I don't know if It's hard to say. Like with most technology, like you said, it's morally neutral and it's really what you do with it, much like any tool. Um, but it also feels like, much like the AI that we know today was bound to happen,
Yep.
and it's going to be used for good and bad. It's just like, it's like a manifest destiny of technology. Like, we want to keep bettering ourselves, much like the singularity. It's not like, if the singularity were to happen, or like on the road to the singularity, is the AI just gonna like sit down and be like, I don't really want to improve myself. I'm pretty good here. I'm gonna lead a hedonist lifestyle until the sun burns out, because I don't need to get any better. No, it's probably gonna keep trying to make itself better, much like humans do, and so it's gonna happen. So it's more like, what are we going to do about it? Not, will we have to do something about it?
Exactly. Because if it's not P equals NP, and it probably won't be, I think the next most likely thing that would have that same paradigm shift, as I mentioned, is quantum computing, and that is way more probable and likely to happen in the relatively near future than
Yeah.
proving P equals NP, and that has very similar ramifications, in particular for things like
Hmm.
cryptography, for all the same reasons. Because effectively, what it's doing is saying, doesn't matter if P equals NP, we can solve everything in near constant time, and that's
Right.
amazing, and will produce just astonishing technologies. But again, in the short term, I don't know how society copes with that. We couldn't deal with a few years of having to stay home.
Right. It's funny you bring up the quantum computing. It's sort of like, if if P equals NP doesn't matter, and it's really just a matter of like bettering, like I said, the hardware and throwing more hardware at it. Uh, doesn't that mean that it's more like, well, then only this mega rich can fix these problems? Whereas if P equals NP, that means that we don't need all the hardware and the money necessarily to solve these problems, because we can, as you say, translate them into easier problems with less hardware, less time, less energy. That's better for like the common person,
Yeah,
but they both have the same kind of ramifications of like, this changes how things are done.
yeah. As soon as if it's possible for the common person to do it, and by common person I mean not the super rich. I don't necessarily mean anyone. I just mean the people who have the mental capacity to do it, but not necessarily the financial.
Hmm.
If they can do this, and P equals NP would be much easier problem there than quantum computing, then yeah, that would be much better for keeping the playing field somewhat even. But quantum computing,
Yeah.
if that ever happens, right now it's going to start just like computers did, right? Being very expensive, very much. You'll probably see them on like university campuses and very rich people's houses, but not anywhere else. But eventually, if you just look at the way technology has advanced, it's likely to just keep advancing, and it will get out to people. And when it does, who knows what the future is going to look like?
Yeah, you make me think of 3D printers. I remember when they were first
Oh
out,
yeah,
that
exactly.
was like, whoa, craziness. You'd have to go to some place and like rent time on someone's one. And then, not that long ago, you can just get a 3D printer at home, and it's like, it's almost like not even that cool anymore, when before it didn't even seem possible. So, yeah, technology's like that. All right. Well, Matt, I think you did an excellent job in trying to break down this concept, which I will agree that it is not a simple, easily digestible concept. But I think the consequences, like you said, are really the important thing. It's like, okay, even whether you understand this concept or not, it's more like, if it is proven, what does it mean? What's good, what's bad about it. But I think even in the explanation, you did a good job. So I thank you for your time going through this meaty subject this episode.
I'm glad you enjoyed it.
All right. I believe that's P versus NP from Mike and Matt this week. Thank you for listening. If you would like more episodes like this, you can get them at hackingthegrepson.com. We are almost to episode 50, everyone.
Gasp.
Uh, I know. I think that's a pretty notable milestone in this podcast's history. So Matt and I are going to try to think of something a little more unique, a little more unusual to do for episode 50. And you'll know what it is when it happens. So until then, we return you to your regularly scheduled lives already in progress.